Arjun sir.
Yeah, I'm here.
Yes, sir. Sir, you present your screen, sir.
Okay, let's just give me a sec. I will share my screen. Can you see my screen?
Yes, sir. Yes, sir. It is visible, sir.
Okay.
Sir, with your permission, we would like to introduce you by reading profile, sir. Yours profile.
Sure, yeah.
Yes, sir. So now I invite Mr. Siddhartha, sir, to introduce Arjun, sir, to session. Thank
Yeah,
you,
thank you,
Siddhartha,
sir.
sir.
Thank you.
Yeah, Arjun, sir, it's the session is over to you, sir. You can start the session.
Sure. Yeah, thank you so much for the kind introduction. And thanks a lot for having me here. I'm happy to be here. I hope I will be able to give you, useful information. So, as you all know, the topic is Introduction to Quantum Computing. I have two sessions, 1.5 hours each, today and tomorrow. So I've divided the material roughly equally, and let's go to the outline. So this is the outline I have planned for the 2 days. Are you able to see my screen and the laser pointer?
Yes, sir. Yes, sir.
Okay. Yeah. Okay. Uh, so I'll start with of course, the question that we are all trying to answer: what is quantum computing? I'll try to answer that in a very intuitive way. Now, as you all know, quantum computing is an extremely broad field. It's very difficult to give a thorough overview, go into the details in 2 days. So my goal essentially is to give you an intuitive overview, not to go too much into the mathematics of the equations, but to focus on the intuitive understanding, so that you have a basic understanding rather than going into the mathematical details. And I'm hoping to do that by comparing it with classical computing, because classical computing is something that we all understand very well. By now we all know what zeros and ones are, and the date and the gates that are used and all. So I'll try to compare it to classical computing. I mean, classical computing, we use bits, zeros and ones. And in quantum computing, we use something called as quantum bits or qubits. So again, I'll introduce qubits by comparing them to the classical bits. I'll go into the nature of quantum computing. Like again, I said classical computing is something that we understand very well, in the sense that when you say 2 plus 3 is equal to 5 or something, we pretty much understand, almost all of us understand how the classical computer does it. When we say 2, we know what 2 is written in, in bits. When you write it in binary, 2 is written as 1 0, and 3 is written as 1 1. So these things are very easy to understand for us. Quantum computing has this sort of impression. A lot of people have this impression that's much more complex, but I'll try to simplify it, and try to compare it to classical computing and have some analogies that will hopefully make it easier for you to get an intuitive understanding of how quantum computing works. So like I said, the smallest feature of quantum computer is the qubit. Just like the smallest building block of a classical computer is the bit. Everything is done using zeros and ones. For quantum computing, we have a qubit. I'll go into the details again. This is just outline. We need a bit of linear algebra for that, but again, I'm not assuming any background. So even if, I know we have all probably gone through that, gone through the basics of linear algebra and quantum mechanics, but even if you don't remember it very clearly, don't worry, because I'm not assuming any background. I'm going to go from the basics up. I think a very important, before that, I'd like to say, I'm going from the basics up. So if there are people in the audience who are more advanced and all, please bear with me. I will be starting with the simple stuff, but as it goes on, I'll try to go into the more complex stuff. Again, there won't be much of mathematics or equations, simply because there isn't enough time to go into it. But I will go, as time goes on, I will go into the more more nuanced details of it. But I will be starting with the simplest stuff. So if there are advanced people in the audience, please bear with me for some time. I think yeah, and I think a very important question with quantum computing is when to use quantum computing. And I think the other side of the coin of that is when not to use quantum computing. I specifically want to discuss this because I see a lot of people, when there's a lot of hype in the field, people tend to very easily say things like there's going to be a quantum computer for everything, which essentially, I'll go into the details of why, but I think that's not necessarily true. So that's why I will go into the details of when to use quantum computing, and most importantly, when not to use quantum computing. I'll go into as you know, quantum computing is in a very nascent stage. We are not, I mean, it can be compared to the early stages of the development of our classical computer. So it's a very exciting time to be, because the technology is just being developed. But that also means there are a lot of unsolved challenges. So I'm going to mention some of them. Hopefully, some of you will be able to solve these challenges. Again, qubits, implementation of qubits, I'll go into the details, but to put it very simply, again, I'll compare it to the classical bit. You know how a classical bit is represented, right? It very simply, it can just be a switch. If a switch is off, it is 0. If a switch is on, it is bit 1. Now, how do you implement a qubit? It cannot, of course, it cannot be implemented as a switch. Then how do we implement a qubit? That's something I will go into. And just like you have gates in classical computing, we also have quantum gates. These are very, very similar to classical gates. As I go into the details, quantum gates will probably come tomorrow, but you will see in the classical gates, we have, and, or, not, and all. So there are some gates which are exactly the same as in classical computing. For example, there is the NOT gate in classical computing, which turns a 0 into a 1 or a 1 into a 0. You have almost exactly the same thing. There is a NOT gate in quantum computing, which turns a qubit 0 into 1 or a 1 into 0. But there are also some gates which are completely different from classical computing, which I will go into in the later slides. So overall, this is the outline that I'm planning. And again, before I start, I'd like to say, if you have any questions, please feel free to, interrupt me right away. I have not, like, there's 1.5 hours today, but the material is much shorter. I kept it deliberately shorter so that there is enough time for interaction and questions. So if you have any questions, just interrupt me right away and I will answer that. Another thing is, I prefer, like, if you ask more questions today. The reason is that gives me time. There's going to be a question that I do not know the answer to. So if you ask me that today, that will give me time to look over it and hopefully answer that too. So that's what I hope you guys learn, and the learning goals that I'm focusing on specifically. The first one is probably the most important one. Like I said, it's in 2 days, it's very difficult to go into the mathematical details or, like, real details. So my focus is going to be an intuitive understanding of what quantum computing means. Now, right away, it's a very tricky thing to do, because as you all know, quantum is well known as a field that is, not very intuitive. It's known as a very mathematical and abstract subject. But I will do my best to provide what is an intuitive understanding. And again, like I said, I'm going to do that by comparing it to classical computers, because that is what we understand very well. Uh, so again, like I said, another focus of mine is what quantum computers can and cannot do. Question, because when we start, working on researching quantum computers, it's very important to, not be overly optimistic and not be taken in by the hype that's surrounding the field these days. Like I said, a lot of people very casually say that quantum computers can solve anything. They can, cure cancer, or, like, break encryption. Part of this is true, but we need to understand the practical limitations of quantum computers. So that's why I always say, like, it's important to know what quantum computers can do, but it's equally important what quantum computers cannot do. So I will focus on that too. And like I said, I'm going to try to compare quantum bits to classical bits, or even, quantum mechanical phenomena to a classical phenomena, just for an intuitive understanding. When there's an analogy, it's always easier to understand. That's why I'm trying to do that. And like I said, there'll be implementations of qubits, quantum gates, and overall, probably tomorrow I will end with an overview of the field. Um, So yeah, on the actual slides of the material, so I'll start with a short history. I always start with this quote by Feynman, which says, "I think I can safely say that nobody understands quantum mechanics." I always start with this quote because it makes things easier for me whenever there's a question that I think one of the reasons, like I said, quantum mechanics has this aura of being a very complicated, abstract and mathematical subject. But I believe that one of the reasons for that is that we do not our everyday experience. And an example of that I always give is when you throw a ball at a wall, one that the ball bounces back at us. So that's our everyday life experience, right? That's what we expect happens, and that's our intuition. So that is explained very well in Newton's laws. Like you have the third law of motion, where it says for every action there's an equal and opposite reaction. So when we are taught Newton's laws, the third law, it's very easy to understand intuitively, because we are used to seeing that every day. But when you have something, a concept in quantum mechanics called quantum tunneling, where you say that if there's a barrier, an electron is able to, the electron doesn't have to go over the barrier. Let me just draw it here. And so let's say there's a barrier here, and there's an electron on this side. Say that the electron gains energy and then crosses the barrier. Pardon my drawing, but when it gains energy, crosses the barrier and goes over, that is sort of, intuitive and it easy to understand, because you can throw a ball over a wall. But there is this concept of quantum tunneling, where you have the electron just tunnels through the barrier and goes to the other side. Now that we find it a little hard to imagine because we are not used to seeing that in real life. When we throw a ball at the wall, we almost never see the ball go through it. That's the reason. But I'd like to point out that it does not mean that it's a vague or it is abstract, but it is very mathematically precise. So just like there's an equation, there's a very precise equation that describes force and mass and acceleration in Newton's laws. There's a very precise in electron. So I'd like to point out that quantum mechanics has this aura of mystery around it, but it is not like that. It is probabilistic, yes. There is probability involved, but it's very precise, and there are exact equations for all these phenomena. So that's something I just want to point out before about quantum mechanics in general. So in 1992, Feynman proposed the idea of creating machines based on the laws of quantum mechanics instead of the laws of classical physics. And then, eventually we came up with Shor's and Grover's algorithm. I'll go on to the next slide. So yeah, like I said, before I go to quantum computing, I'd like to start with classical computing again, simply because that's something we understand very well. So I'm going to use that as a base and build up quantum computing. Just give me a minute, 1 minute, I'll be back. Yeah, sorry. Going back to classical computing, so we all know that classical computing uses zeros and ones, which in our case can be represented using transistors. So for example, a transistor can be on or off, and the on and off states can be represented by bits 0 and 1. Computing power in case of classical computing, as increases linearly with the number of transistors. I've written this here because you will see that in case of quantum computing, computing power increases exponentially with the number of qubits. That's one of the biggest reasons for the speed up that quantum computers can give us. Again, I'll give the details will come later for why classical computing increases linearly, whereas quantum computing goes exponentially with the number of qubits. So another thing is that I think will come in the challenges is, as you all know, classical computers have low error rates. For example, if we write some data into a pen drive, it essentially is writing zeros and ones. Even if we read the pen drive after several years, essentially we have our data. We do not lose the data. We are used to having, writing our data in a hard disk or a pen drive and having the same data back to us for several years. Whereas you'll see that in case of quantum computers or qubits, we are lucky if we have the data undisturbed for few micro milliseconds. So I'll come to the reasons for that too, but I just like to point out that classical computers have very low error rates compared to quantum computers. And the other thing is classical computers can operate at room temperature. We don't need to cool them. Quantum computers require cryogenic cooling. I'll again come to that in the next slides. And most everyday processing is best handled by classical computers. Most of the things that we need to do these days, like, whatever it is, like games or computations or, word processing, this presentation, anything. Most things are handled, very well by classical computers. There are only specific problems where classical computers have a lot of problems. And examples of these are, an example that I can come up with is factoring large numbers. These sort of problems we will come to why exactly, but these sort of problems where classical computers struggle, some of these problems can be handled very well by quantum computers, and that's where their real power comes in. So yeah, before I go into what exactly quantum computation is, I'd like to introduce the idea of quantum computation with a game. The game is known, I don't know if you guys have heard of it. There's a game known on American game shows as Plinko. Before I go on, are there any questions so far, or can I continue? Because this section might take a while. Okay, I guess no questions, so I'll continue. This game is known to mathematicians as physicists as a Galton board. So again, it is a game, but bear with me. I'm using it to illustrate the idea of how quantum computing works. So and I think if you get an understanding of this phenomena, it gives you a very good intuitive feel for why quantum computing works and why it's so fast compared to classical computing. So I mean, please do pay attention to this. This is a very interesting concept, and it illustrates the exponential versus linear speed up very well. So the idea is quite simple. The game is like this. You have a ball dropping from top, and it meets a number of pegs. So let's say the ball starts from there and meets this peg. When it collides with this peg, it can go in two directions, and it has equal probability of going in either direction. So it goes in direction. Again, it meets this peg, and it goes in either direction, this direction, and so on. At every point it meets an obstacle, it has two paths it can go in, and it goes on either one with equal probability. So finally, when the ball drops, it will drop into one of these one of these containers at the end. When you drop multiple balls, you will have positions like this. Some containers may have some no balls, or most containers in the middle will have the maximum number of balls. So essentially that's the game. You drop various balls from top, and then you have these balls dropping into various containers here. This is an animated example just to make it more clear. And this is another huge number of balls here, just showing the distribution. Someone has anyone heard of this, or would someone like to say what this distribution is? The ball, you can see clearly in the center the balls are maximum, whereas in the corner you have the minimum number of balls. Does anyone know what the distribution is of balls? It's a normal distribution, right? It's like a bell curve. So it's sort of it's actually a binomial distribution, but when you drop these balls, most of the balls tend to center around the center. But now, why is this important for quantum computing? I will come to that. That becomes clear. So let's say instead of having balls, let's use photons. So the idea is this. Again, we are taking a simple system. In the original case, let's say two-level system. The ball drops here. It meets an obstacle. It has two directions it can go in. Let's say the ball comes here. It has two directions it can go in. So overall, it has three can fall into. If we replace the ball with a photon, and we replace these obstacles with a beam splitter, we essentially have the same kind of setup. The only difference is that you have a photon coming over here. There is a beam splitter here, and the photon has equal probability to go in either direction. Let's say the photon comes, hits the beam splitter, goes in this direction. It meets another beam splitter, and it has equal probability to go in either direction. Let's say it goes in this direction and comes over here. The only thing we have done is we have replaced this mechanical, balls falling with photons being split by a beam splitter. Now we have remade the game with quantum objects. Photon can be considered as a quantum object instead of balls. So with a single photon, the game behaves exactly like the mechanical version, because in the mechanical version you have a single ball, it bounces around and then falls into containers. It's exactly the same when you have a single photon. A single photon comes, it gets moved around by the beam splitter and goes into one of the detectors. When you have two photons, that's when things get interesting. Now you all know what interference is, right? There is constructive and destructive interference. Now, when you have two photons come in, and they, let's say, as in the case of this diagram, they meet at a point. Whether they interfere constructively or destructively depends on the path they have taken, right? So that's when things get interesting. But to calculate, let's say I want to calculate, let's say both the photons reach here, reach this point. Do they interfere constructively or destructively? If I want to calculate those things, the only way I can do it is trace all the paths that the two photons can take, right? I'll pause here for a minute to let that sink in. So let's say I want to calculate whether the photons construct, construct, interfere constructively or destructively at this point. The only way I can know that is by actually calculating the possible paths that the two photons can take. That's the only way I can calculate it, right? So the point I'm trying to make is to predict the end state of a quantum object. We need to manually calculate all these paths and then count, the distance that each photon has taken. So the point is that let's say I do not have this machine with me. I do not have this beam splitter with me. I just have a piece of paper and pen with me, and I want to calculate this. The only way I can do it is to individually calculate these paths, find the difference, all the paths the photons can take, and then the path difference between them, and then I can find out whether they interfere constructively or destructively. That is one way to do it. Now we look at why this becomes more complex. This is the most simple example that we have taken. There are only two levels, but it becomes more complex when you add more levels, right? So again, we'll start with the simplest example. We have two rows of beam splitters, two photons. We'll count it for the simple case. Each photon can take four different paths, right? I'll count out the paths. It goes here. This is one path. Again, it takes this path. This is the second path it can take, this way, and over here, and this is the third path. It goes down, it comes here, and this is the fourth path it can take. So when you have a two-level beam splitter like this, each photon can take four different paths. If you have two photons, then each one has four paths, and you have 4 into 4, that's 16 different combinations that are possible. Now that's an example of classical computing. This is how classical computers calculate. Actually, if you have, let's say, 4 bits, you can have 16 different combinations of the 4 bits, and each of those has to be done one by one. And as the number of levels or the number of bits gets larger, the complexity increases, as you can see in classical computing. So let's say, for an example, that calculating the interference for each one takes TC seconds. Then for a two-level game, as we saw earlier, there are 16 possible paths, and it takes 16 TC seconds, say, to calculate all the possibilities for it using pen and paper. Similarly, for a three-level game, you have 64 possible paths, and it takes 64 TC seconds if I want to calculate all the possibilities using pen and paper. Or, I'm calling it the pen and paper method, but it's similar to the classical method of doing things. Now, where does the quantum way of doing things come? So let's say, as we see, as the game gets larger, there is more interference, there's more complexity, it takes longer. So let's say that so instead of actually using pen and paper, let's say we actually build this system. I actually have a beam splitter. I have all these beam splitters. I set them up. I have a source of photons, and I keep a detector over here. Instead of each of the bins for the balls to fall into, I have a detector that detects photons. So when you shine light over here, the beam actually, now I'm not using pen and paper here. I've actually set up the optical experiment. I have a source of photons. I have these beam splitters set up here, and I have these detectors. All I have to do is shine two photons, repeat the experiment number of times, and I get the number of, if I count the number of times the photons hit a particular detector, I get the count over here. Now let's compare the time. Now we all saw how the complexity increases when I use the pen and paper or the classical method to calculate the number of parts. Now let's do the same for how the complexity grows when I'm actually doing the experiment in this way. So let's say for each of the levels, the sampling time it takes to traverse the gap is tq. So when you have a two-level system like this, the photon only has to cross two gaps, say this gap. Yeah, this is a three-level system, so there are three gaps. But for a two-level system, it takes two gaps, so it's 2 TQ seconds. And for a three-level system, there are three gaps, so it takes 3 TQ seconds. So so you can immediately see that the complexity doesn't grow as fast as for classical computing. Uh, to compare the complexity, I'm just summarizing it again. So for each layer, the number of parts uh, to consider in the computational simulation increases by a factor of 2. So in let's say you have an n layer system instead of 2 or 3. There are 2 raised to n paths that each photon can take. So in case of the classical case, when you had to compute each of those individually, one by one, you would have to count. Let's say this is one path, this is the other path. The number of possibilities for an n-level system was 2 raised to 2n in case of a classical way or the pen and paper method of doing it. But when you come to the quantum way of doing it, sorry, there's a mistake here. This should be n. When it comes to the quantum way of doing it, the speed up, again, this is probably the crux of the matter, or like place where the speed up actually happens. Now, speed up happens because when you actually build the system, you don't have to do, manually calculate the path. All you do is let a photon drop. It does its thing. It goes on the path it wants to go. All you have to do is count where the photon lands based on the number of detectors. And the complexity grows only by the number of levels. It doesn't increase exponentially. You add another level, it just increases linearly. So you have n into tq system. So I hope I managed to explain, this is the last slide with this complexity. After that, I'll pause if you have any questions. But please try to understand this, because this is very important to understand why quantum speed up is possible. So in case of the classical system, it increases exponentially with the number of levels. You have TC and you have n number of levels. It increased as 2 raised to 2n. Whereas when you actually built the system, you actually had a beam splitter in there. The complexity only increased by n. So if we put in some numbers and generously assume that each computation, the classical way, takes only 100 microseconds, and even if the detector takes 10 seconds to detect a photon, you will see that very quickly the classical way of doing things is much slower. The classical way of doing things is much slower than the quantum way of doing things. So in this green line here is the quantum time. So as the number of layers increases, the amount of time it takes a quantum computer, the quantum way of solving things, increases linearly, whereas the classical way of doing things increases exponentially. So of course, when the number of layers is very low, let's say it's 1 or 2, the classical computer is still much faster than the quantum computer. But as the number of layers increases, the classical time taken increases exponentially. And you can see in this example, for example, it takes about 10 layers, where at 10 layers, actually, in this case, the classical way of doing things begins to take longer than the quantum way of doing things. So again, the reason I brought this example is because when you have a quantum computer, a lot of people say because it does things in parallel. Now, what do you mean by it does things in parallel? I think this example is a very beautiful example to illustrate what you mean by a quantum computer does things in parallel. So when you like what is happening in parallel here? All that's happening in its parallel here is that the photon is able to, pick its path and go through the level on its own. You do not have to, count the paths one by one. So that's what when you say a quantum computer is able to do things faster because it does things in parallel. This is a very beautiful analogy to explain that. So I hopefully I managed to bring out that intuition as to why quantum computers and their parallelism helps to speed up things. And I hope this also illustrated why when I said in case of a classical computer it grows the processing time initially with a classical computer, whereas with a quantum computer the processing time increases linearly with complexity. So once you have the necessary number of qubits, a quantum computer is going to be faster than a classical computer. Uh, Before I go on, probably I'll stop at this slide before. This is the last slide before I'll pause. So this is again, I brought this example to, compare a classical computer versus a quantum computer. The pathfinding calculation where we went through, calculating each individual path. That's exactly, very analogous to the way a classical computation is done. And the beam splitter approach, like I said, it's actually like setting up, an optical experiment. It's more like, setting up a laboratory experiment. But you can see that both methods actually produce the same information, or both methods are actually solving the same problem, whether the photon is interfering constructively or destructively. So if you say that, the pen and paper method is a computation, you can also say that the laboratory experiment is also a computation. The only difference is that as the number of levels increase, the experiment or the quantum way of doing things gets much faster as n or the number of levels increases. So I'll pause here for a couple of minutes to let that sink in. Or the next section is, a slightly different topic. But are there any questions so far on this, or did that analogy make sense? Yeah. So again, I mean, like I said, feel free to interrupt me at any point if if you don't understand anything. But I hope that it gives you an idea of what you mean by parallelism in a quantum computer. And people say this a lot. A quantum computer computes all possible bits at the same time. Like, a quantum computer is able to consider all possible solutions at the same time. But this is very similar to what actually happens in a quantum computer. The only difference is here you have photons and beam splitters. You would have qubits and their computations instead of a beam splitter. Uh, just to give an example, instead of a photon, you might have an electron in a quantum computer, and instead of a beam splitter deciding which way the photon goes, you might have a quantum gate deciding which way the electron goes. But sort of the intuitive explanation for why a quantum computer does things in parallel and why the speed up is so significant when you have a huge number of qubits. So yeah, if there are no more questions, I will go on to the next topic. The next one is again using another an analogy to explain. So quantum computing is a lot like computing using physics. So like in this case, for example, the classical computer was using a pen and paper to calculate all possible paths. Whereas the quantum computer way of doing things was just using an optical setup like a beam splitter and actually doing an experiment to do the computation. So it is sort of like computing using physics. So what do we mean by computing using physics? I'll give another example. This one will be much shorter than the first one, but I hope this reinforce the point of what I mean by computing using physics. Now, a lot of quantum computing is just computing using physics. So this is a problem. The problem is, let's say you have these, you have a number of holes in a shaft like this. The hole is the one I'm pointing to here. You have a number of holes, and you need to cover them all, like this green sheet over here, let's say a rubber sheet, and you need to cover them all with a single piece of sheet using the minimum, surface area of rubber sheet. Now, when you, I'll pause for a minute and let you think about that. How would you go about it? The problem is, problem is simple to state. You have a shaft with a number of, holes in it. You need to cover all of them with a sheet. It has to be a single piece of sheet. So, and the other constraint is you have to use the minimum possible area of the rubber sheet. Now, it's not very easy to, the problem is simple to state, but it's not very easy to, visualize it or solve it, especially if the geometry is complex. So the problem is find the least amount of material required to drape between the constraints. And as you can imagine, the solution is not, computationally, it's not straightforward. You might need to use, complex simulations or try various combinations if you want to do it the classical way. Typically, a lot of fluid computations happen this way. Is there a simpler way of doing it? I'll pause here for a couple of minutes. Does anybody have any ideas on how there might be a simpler way of doing this? Okay, I'll provide the answer. So it's something probably we have seen in everyday life, but it doesn't really strike us when we look at it this way. It's a soap bubble. So when you have, let's say, in this case, two holes, and as you all know, because of surface tension, the soap bubble tends to take up the minimum possible area. So it essentially solving the same problem. So in this case, this is again a beautiful example to show how we can use the laws of physics to find the minimum energy solution. When you put it in its fundamental terms, all that it is a minimum energy solution. A soap film takes up on the minimum possible area and covers the whole, covers all the holes because it tends to minimize its surface tension. And that's essential here. So again, in the case of the beam splitter experiment, if we actually set it up, if we set up wires like in the same shape of the problem that we want to solve and immerse it in a soap bubble, we will have, the solution to the problem. Again, it's sort of like using the laws of physics or surface tension to find a minimum energy solution. A soap bubble always minimizes the surface area. I think quantum computing is very similar to this. And essentially, it uses the laws of physics to minimize the energy. So again, I gave this example because the fact that it minimizes some energy to arrive at a solution is very important. Quantum computing essentially, pretty much is all it does is that, except that in case of instead of a soap bubble, you would have probably electrons or photons. Let's say you have 10 electrons, and you let them, you let them reach it, and the state that you find them in, that's the solution to the problem. So the reason I illustrate this is quantum computing is a little different from classical computing. In case of classical computing, for example, you can have a gate. Let's say you drive zeros and ones, and then the gate computes zeros and ones, and then it gives you the output. In this case of the soap bubble, say, for example, you're not really forcing the soap bubble to do any computation. The soap bubble is, going about life as it wants to go, and just on the way it happens to solve a problem that we are interested in. The soap bubble is just obeying the laws of physics, but we have set up the problem in such a way that the minimum energy solution that it reaches is a solution that is useful for us. So that's something very important to keep in mind, because quantum computing in many, you cannot design it the way you can design a classical computer to do things. Like if you have an electron, all it's going to do essentially is reach its minimum energy point. It is our duty to, frame the problem in a way such that the minimum energy solution that the electron reaches is something that's useful to us in, practical life. So that's the reason I wanted to illustrate this. to give an intuitive understanding of what we mean by computing using quantum mechanics or computing using physics. So yeah, I hope that this sort of gives you a feeling for what we mean by computing using physics. Are there any questions so far? So I think with that understanding, before we actually go into solving quantum computing problems, I think we need to ask two questions. Um which of our classical computation problems have a quantum aspect, and how can we efficiently map that problem onto a quantum system? I think this is very important when you try to solve a problem using a quantum computer. Like I said, the photon just goes about doing its business, or the soap bubble just goes about obeying the laws of physics. It is our duty to map that problem properly so that the solution that emerges is something that is useful for us. So I think these are questions we need to ask, and this is something that to ask in a classical computer. We don't have trouble framing, mapping a problem into the system in classical computer. These are problems that come when we start using quantum computers, or start using physics to solve, do computation. So yeah, with that, I'd like to say, when you ask the question, what is a quantum computer? I think a lot of you would also be able to answer that now. A quantum computer is essentially a machine that performs computations based on the laws of physics, or in this case, it's a quantum computer, so it performs calculations based on the laws of quantum mechanics, which is the behavior of particles at the subatomic level. So, I mean, in a way, the two examples that we saw, they are also, you can call them, they're not quantum computers, but probably like, physics computers. The first one that we saw is, an optical experiment. So it's probably, computing using photons. And the second one was more classical. It's, computing using a film of soap. In case of a quantum computer, again, we do computing using, maybe electrons or photons or whatever. But the important thing is the laws of physics that are used to solve a problem in a quantum computer, the laws of quantum mechanics. So just compare, summarize the differences between classical and quantum computing. In case of classical computing, we know very well you calculate using transistors, which can be 0 or 1. A quantum computer computes using quantum bits or qubits. And again, it's often said that quantum bits can be 0 and 1 at the same time. I'll go into the details again, but I think when you say a quantum bit or qubit can be 0 and 1 at the same time, so it's a bit of a mistake to say that. It's sort of like a combination of 0 and 1. But again, I'll come into the details later. As we saw in case of a classical computer, as the number of, again, don't get confused between computing time and power. In case of power, classical computing, the power increases linear number of transistors, but in case of quantum computer, the power increases exponentially with the number of qubits. In case of time, it's the other way around. The computing time increases linearly with the quantum computer, and the computing time increases exponentially with the classical computer. So again, as I mentioned before, classical computers have very low error rates. The example is, you write into a pen drive or this thing, and you have your data with you even after several years. Quantum computers have very high error rates, and as we will see in the future, we'd be lucky if we are able to maintain a qubit for a few milliseconds. Again, this was the point I mentioned before. Most everyday processing is best handled by classical computers. So whether it's gaming or computing or simulations or any document or a PowerPoint, most of these things can be done by classical computers. The point is, a classical computer is a very good general purpose computer, whereas a quantum computer is well suited for tasks like optimization problems. Now, again, this is where, if you remember, I said in the beginning, people tend to casually say things like a quantum computer can be, in the future, quantum computers will do everything. I tend to, look at that with a bit of skepticism, because like we saw, a quantum computer is not necessarily a good general purpose computer. It can be a very good special purpose computer. I mean, again, going back to the examples that we saw, the photon computer that we built, or the computer that we built with the soap film, they can't be used to do general purpose stuff, right? They do a specific problem very well. Computing where the ball falls is if the photon computer can do it very well. But if you give it some other problem, it's going to struggle a lot. Even the soap film, if you want to find the minimum surface area required to cover a surface, the soap film computer is going to able to do that very quickly. But if you give it any other problem, it's not going to be able to solve that. So the same holds true for a quantum computer. And as you can probably see, quantum computers are very good for optimization problems. The soap film is a very good example of an optimization problem. That's why it's all, whenever when there is energy minimization, it is an optimization problem. So you'll see that quantum computers are excellent for optimization problems, but they may not always be a good solution for general purpose computing. So what people feel is that, just like in our classical processor, like the Intel Core i5 or whatever, these are general purpose processors. And on the side, you have a graphical processing unit, GPU, that only deals with the graphics processing part of it. It is possible that in the future, you only have, a quantum processing unit on the side that only deals with, the quantum problems of it. So the point of this is, a quantum computer is not necessarily a good general purpose computer. That's the point I want to bring out here. It is very good for specific problems. Optimization problems are a very good example, but quantum computers are not good general purpose computers. That's the idea I want to bring out here. So yeah, with that, any questions so far? I'll be starting with qubits now, but any questions so far? I think it's been almost like 45 minutes. It's about halfway through. So do you guys want a break for a couple of minutes, or can I continue? This would be a good point to pause for a couple of minutes.
Sir, am
Yeah.
I audible?
Yeah, you're audible.
Sir, I have a question. You talk about complexity, that time complexity is reduced in a quantum computer. But as a computer, we have a think about the complexity on two bases. That is a space complexity and time complexity. So, what about the space complexity in a quantum computing?
Sorry, I'm not familiar. What is space complexity? What do you mean by space
Means
complexity?
when a program or when any task is executed, some space is utilized for execution. So
You
whether
mean
that
in terms
space,
of, yeah, and any other questions? Do you guys want to break for a couple of minutes, or can I continue?
So continue, sir. Continue, sir.
Okay, I'll continue. Okay, so like, yeah, again, we'll start with the qubits. Like I said, a classical bit. Again, I'll start with the classical bit and move on to the qubit. So a classical bit, we understand it very well. It's a 0 or a 1. And there are various ways you can represent a classical bit. It can be a current in a transistor. It can be a voltage on a capacitor. Like, in case of hard disk, it can be a magnetic domain. Essentially, any two-state system, any switch where you can have two states can be used to represent a classical bit. Now, how do you represent a quantum bit or a qubit? Again, it's any two-level quantum system. An electron, if you have an electron and it has two levels that it can go to, it can be a quantum system. You can use a photon. You can use, traps in materials as quantum bits. There are various systems you can use. Like, just like for a classical bit, you can use various things to represent a classical bit. There are various ways you can represent a quantum bit. We will look at the various ways and their, advantages and disadvantages in the future. But at this point, all I want to say is the only difference between a classical bit and a quantum bit is that a quantum bit is a two-level quantum system. And again, when people say that, quantum bit can be same time, it's a technical mistake to say that. Give a good example. An example is a coin. You have heads and tails on a coin. A coin can be heads or tails. But when the coin is spinning, or let's say the coin is being flipped, what can you say that the coin is both heads and tails at the same time? It's technically not correct to say that the coin is heads and tails at the same time, right? It's sort of a combination, or you cannot define what the state is in that position. So that's an example I can give to say what they mean by saying a combination of 0 and 1. But yeah, I'll give a better. I mean, yeah, that was an analogy, but I'll also give a better example of what I mean by superposition. So actually, like I said here, a qubit is a vector in a 2D complex vector space. Yeah, there's no slide here, so for that, so I will draw it and explain it. The idea is, let's say you have a 2D. Let me go to the pen. So let's say you have a 2D plane. Again, pardon my lines, but they're supposed to be straight lines. So this is the y-axis, and this is the x-axis. Let's say you have two states of a qubit. They are 0 and 1. So let's say when the qubit is in 0 state, this is the state. I'm just pointing out here. Let's say it's at a distance of 1. This is the origin. Yeah, this is the origin. So let's say this is represented as the 0 state of the qubit. And when the qubit is in state 1, let us say it is on the y-axis over here. So this is state 1 of the qubit. So again, at this point, you don't have to worry too much about what 0 and 1 mean. You can assume it's very similar to the classical 0 or 1. So when a bit is at this point in this 2D plane, and when a bit is in the 1 state, you can assume it's at this point in the 1 state. So again, very similar to the way you use complex numbers or real numbers. If you have a real number 1, then it would be at this point, right? 1 would be over here. And if you have an imaginary number I, it would be over here. Now the interesting thing about qubits is, now the thing with classical bits is it can only be 0 or 1. That's the thing. The thing with qubits is that it can be a combination of the two. What I mean by that is it can be a vector in between as well. So let's say it is somewhere here. A qubit can also be over here. In that case, as you know, there is a 0 component to the qubit, and there is also a 1 component to the qubit. So it can be in a state that is, this is what you mean by superposition. Superposition or a combination of 0 and 1 essentially means, a vector combination of 0 and 1. So let me use the laser pointer again. Yeah, that's all that it means. So superposition essentially means, or a combination of 0 and 1 means a linear combination of 0 and 1. So in this case, let's say the qubit is in this state, then it has a 0, like, a percentage of it. Let's say this is 45 degrees. Then, 1 by root 2 of it is in 0 state, and 1 by root 2 of it is in 1 state. And as you can imagine, it has to be a unit vector. When you calculate the magnitude of it, it has to be 1. So I hope that is clear, what I mean by superposition, a combination of 0 and 1. So again, just to say, classical bit can only be 0 or 1, but a qubit can be like a vector, and it's like, a linear combination of 0 and 1. And that is what actually is meant by superposition, a combination of 0 and 1. So again, it is very, when you say that a qubit is here, it is wrong to say that a qubit is both 0 and 1, because, when you look at it as a vector, you cannot say it is both, it's a linear combination of the two. So, please keep that in mind. This is a very fundamental thing to keep in mind. You should never say that a qubit is both 0 and 1, just like you wouldn't say a vector is both x and y direction. I mean, just like you cannot say a vector is both, unit vector in x and unit vector in y direction. It's a linear combination of a unit vector in x and a linear and a unit vector in y direction. So just like that, a qubit is not both 0 and 1. It is a linear combination of 0 and 1 states. And like I said, a vector, just like I've drawn here, a vector it is a vector in a 2D complex vector space. So I've drawn only real terms here, but actually, you can have complex coefficients as well. I have drawn only the real parts here just to illustrate it, but you can draw it as a 3D diagram with complex coefficients as well. So I hope this concept of a qubit is clear. The only thing to take home from this is a classical bit is 0 and 1, and a quantum bit can be a linear combination of the two. That's all there is to take home from these 2 points. So just like a classical bit has certain requirements, you need a few requirements for a qubit. Like again, you can imagine them from the classical bit examples. You need the ability to initialize. So just like if you make a classical bit, you would want the ability to set it to 0 or 1. Similarly, when you have a qubit or a quantum bit, you would want the ability to initialize it to 0 or 1. So that's essentially one requirement you would want in a qubit. Long coherence times, again, I mean that let's say you set a bit to 0 or 1, you would want it to remain that way as long as possible and not, randomly change values. So in case of classical bits, we have gotten very good at doing that. For example, you keep a charge on a capacitor. If you isolate it, it will hold that charge for a really long time to come. But unfortunately, with qubits, it's very difficult because, as you can imagine, they are quantum systems. They are very delicate and, susceptible to environmental noise. So it's very difficult to have qubits with low error rates. And the minimum that you would need is that the qubit holds state 0 or 1 for as long as it takes to, do the gate operation on it. That's why I said when we say long coherence times, we would like as long as possible, but the minimum required is that it should at least hold its state for as long as it takes, the quantum gate to do an operation on it. The other requirement for a qubit is that it has to have, the ability to make quantum gates. Just like if you make zeros and ones using a transistor, using some logic, let's say, CMOS or NMOS logic, using the same logic, you would want to build, classical gates, not and you would, if you only have the ability to make 0 and 1 and don't have the ability to make gates using the same technology, then it isn't of much use. Similarly, if you just have the ability to make a quantum bit and do not have the ability to make quantum gates using that technology, then it is not of much use. So another requirement of a qubit is that you need to have the ability to make working quantum gates using that technology. Another requirement of a qubit is that you need to have measurement capability. So again, when you have 0 or 1, we need a way to read that 0 on 1. Typically in a transistor, you read the current and figure out whether it's on or off. In case of a qubit, again, you would have various ways of doing that. But whatever the state of the qubit, you need a way to read that, and figure out what state the qubit is in. So it's important to have the measurement capability for a qubit. And yeah, again, most important is scalable. As you all know, with technology, the number of transistors on our chips have kept increasing and increasing, and that's a big factor in the progress that we have made. Now, when you make a qubit technology, it's important to keep the future in mind and make sure that it's scalable. For example, we had very good vacuum tubes, but they became obsolete now because we were not able to scale them as fast as solid state transistors. Whereas once we made, we had semiconductors and solid state transistors, we were able to scale them very fast. You could make ICs, and add more and more transistors on the same chip, and as you all know, the computers that we have keep getting faster and faster. So scalability is a big factor in the success of a technology. So whatever qubit technology we have, we need to keep in mind the future and make sure that able. Now, qubit implementations is something that I will go to probably tomorrow. But like I said, that is again, like the way you have various ways to represent a classical bit. There are various ways to represent a qubit, which I will go into tomorrow because it's more of So yeah, again, what is a qubit? A bit of a repetition, but I'll go through this slide again. Uh, Again, it's just a two-state quantum system, and I represent them as 0 and 1. Sorry, I should have mentioned this before. This notation is just called as a bracket notation. Nothing special about it. You don't have to think too much about it. It's just a bracket note. It's called bracket notation and typically used to represent quantum states. So it's just a vertical line, followed by this greater than sign. So you represent 0 and 1 using this notation. But this is the way we represent quantum bits. And like I said, a physical implementation of a qubit can use any two-level quantum system. An example of a quantum system is the energy levels of an atom. So for example, let's say the electron is in this lower energy state. You can say that it is in state 0. And then, you shine light on it, the electron goes to a higher energy state, and you can say that it is in state 1. Again, very similar to the way you have states 0 and 1 in a classical computer. Let's say you have a capacitor, it's discharged, it is in state 0. It is charged, it is in state 1. The only difference is in case of a quantum qubit, you use a quantum system, a two-level quantum system instead of a classical system. So yeah, again, this is, I think we have already gone into that. The classical bit can be represented as 0 and 1. Again, I'll repeat the point. Classical bits can take 0 and 1 and nothing in between. But a quantum bit, and this is very important, that's one of the biggest reasons for why we are able to use quantum states. A quantum bit is not just 0 and 1. It can be any linear combination of 0 and 1. So that's one of the biggest, one of the biggest reasons for the power of quantum computers. They are not just stuck at 0 and 1. They can be any linear combination of 0 and 1. Like I said, it's not just real coefficients. You can have imaginary coefficients as well. So again, yeah, I already mentioned the Ket notation. But yeah, like I said, I drew a 2D picture earlier, but since you have, complex coefficients as well, they can be represented on a 3D globe like this. So again, these details are, but this is just to illustrate. If you have 0 and 1, you can go in all directions, not just a 2D map, because you have real as well as imaginary coefficients for it. So like I said, just like a bit is the fundamental unit for classical computing, qubit is the fundamental unit of quantum information. And all our computations are based on the manipulations of qubits. And it's very similar to classical computing. When you go down to it, essentially all classical computing is just doing manipulations of classical bits. And any computation essentially is just changing 0 to 1 or 1 to 0 using logic gates. Similarly, any quantum computing essentially is just doing manipulations of qubits using quantum gates. So like I said, qubits can be implemented in various ways. A couple of examples that we saw, using a photon. Now, there are various ways to do it. The current, probably the leading technology is using superconducting qubits, but there are various ways to do it. You can have nuclear NMR qubits, you can use traps as qubits. There are nitrogen vacancies in diamond that can be used as qubit. Even electrons, so the electron spin can be used as a qubit. Any two-level quantum system that meets the requirements that a qubit has can be used as a qubit implementation. The details of these and the advantages and disadvantages of each, I will be going into them tomorrow. But this is just to list the various implementations that we have. So yeah, like I said, one thing we need to keep in mind is when to use quantum computers, and more importantly, when not to use quantum computers. So again, I already mentioned this, but I'll mention it again because I think it's very important to keep this in mind when we approach a problem in quantum computing. There's a lot of hype surrounding the field these days. There's a lot of enthusiasm. It's good, but when people say things like, like I said before, when people say things like a quantum computer, everyone is going to have a quantum computer, like quantum computer is going to solve everything. You need to take a look at it with a bit of skepticism, because like I said, like we saw in the example of the photon computer or the soap film computer, they give speed up only for very specific problems. The good thing is these problems are typically very hard and intractable, but please keep this in mind that quantum computers are usually good only for very specific problems. Optimization problems are a very good example. A very good example of problems which are very good for quantum computers. An example is cryptography. So, yeah, as you all know, all cryptography is based on the fact that it is very difficult to factorize a huge number. So, if you have a huge, let's say, a very big number, it's very difficult to find its prime factors. But this is an example of a very difficult problem. A classical computer has a very hard time solving it, but it's very easy. It's much easier to solve that problem using a quantum computer. There are algorithms known as, an example is Shor's algorithm, that can solve this problem much faster using a quantum computer. And that's one of the reasons there is all this hype that if you have a quantum computer, you'll be able to break cryptography. The problems which are very good to solve using a quantum computer. And in fact, it's very we are lucky that there are these problems which are hard to solve, but they are very good using a quantum computer. Examples of these are quantum search, and like I said, optimization. Optimization is a very broad field, which is why I keep mentioning it. And I'd like to reiterate that the reason for this is, again, revisiting the soap film problem. All that the soap film was doing was minimizing the surface tension. So again, very similarly, when you have a quantum computer, all that the electron does is goes to its minimum energy state. So if you can map an optimization problem onto this, then the electron just goes about doing its business, but in the process you have a solution for your problem. Just like the soap film was just going about doing its business, but in the process we got the solution to a problem. And that's why optimization problems are very good for quantum computers, because all quantum computers do are energy minimization. And there are various other examples like finance forecasting, protein folding, and drug discovery, and so on. So the point of this is it's very important to keep in mind when to use quantum computers and when not to use quantum computers. So yeah, some of the challenges with the quantum computers are, like I was mentioning in the previous slide, is that speed up is possible only for specific problems. So it's very wrong to say things like quantum computers can do everything very fast. And again, like I said, most probably, currently the consensus is, no one knows the future, but what we would probably most expect is, just like currently you have a graphical processing unit next to a general processor, and the graphical processing unit or GPU takes care of only the graphics part of it. In the future, you may have like a QPU or a quantum processing unit that takes care only of the quantum processing tasks. So again, I'm just reiterating, a quantum computer is not a good general purpose computer. It is good only for specific problems. Another problem with quantum computing is there are very stringent requirements for the environment. So like I said in the beginning, a classical computer doesn't read, you can use it at room temperature. But the problem with with a quantum computer is that it requires cryogenic cooling. And, I think you can understand why. Let's say you have an electron. uh, there's very little energy that an electron needs to jump between levels. So if that is your quantum system, if your quantum system is just an electron between two levels, then any temperature fluctuations or anything can give enough energy to the electron. It can move about and change its state. So that's not something you would want, right? So typically, most of these quantum technology implementations require cryogenic cooling. They go to almost to several millikelvins of temperature, very close to absolute zero. So the problem with that is that these cryogenic cooling technologies are not very compact. you have very big systems. I had a picture here, maybe it's there in the next slide. Yeah, like this. So, this is an example of, a dilution fridge. This is typically what a quantum computer looks like. This is called as dilution fridge. And you can see it's not pocket friendly. When you say, again, when someone says things like quantum computers are going to be there in our mobile phones, it's not, I mean, I can't say it's not going to happen, but it's going to, there are a lot of problems to get there. The first thing is, how are you going to pack this into your pocket? That's a big problem. So it is not pocket friendly, and by that I mean two things. One, it's not something that might, in the near future be compact or fit into a pocket. And the other thing is, it's not pocket friendly in the sense, I mean, it's not going to be very cheap. It is quite expensive, as you can imagine. And another big challenge of quantum computing is quantum error correction. Again, building on the same point I mentioned, it's very difficult. As you can imagine, typically, quantum system is, let's say, an electron. It's very easy to disturb an electron, right? And any temperature fluctuation can disturb an electron. So quantum error correction is again a big field of research. There's a lot of work going on, and it looks like without good quantum error correction codes, we are not going to be able to do, useful quantum computing. And sorry, just a sec. Yeah. Yeah, sorry. So the last challenge is, like I said, is scaling up. And again, to see an example of it, we only have to go back to the way our classical computing has progressed. Vacuum tubes were what we had first, but as you had solid state transistors coming up, vacuum tubes, we barely see them anywhere. And one of the biggest reasons for that is scaling. With solid state technology, you can have integrated circuits and you can really scale them up. You can add more and more transistors on the same chip and make it more and more powerful. Whereas with vacuum tubes, it became more and more difficult to do that. So the same thing, technology can be very good, but if it doesn't scale up well, there's a good chance that it becomes obsolete in the future, as happened with vacuum tubes. So I mean, yeah, that's mentioned as a challenge because sometimes, when these early stages, we tend to think only of the best technology, but it's important to keep the future in mind and see whether the technology is capable of scaling up. So, I mean, in a sense, I guess I'm nearing the end of today's section. So, in summary for today, tomorrow I'll deal with the rest of the things that were not covered in the outline. But for today, in a way, I would like to summarize by saying that in a real sense, quantum computers do not compute at all, but simply carry on according to the laws of physics. So again, you just have to go back to the example of the soap film to understand this point. So the soap film doesn't really care about us or our problems, or doesn't really listen to us. All the soap film is doing, it's going about obeying the laws of physics. And it is our responsibility to map a problem onto that, so that when the soap film finds its minimum energy point, it is solving a problem that is useful to us. So to that, I mean, the extent to which quantum computing can revolutionize computation depends on our finding ways to restate computational problems in equivalent quantum systems. So as you saw, we were able to, in the first example, the problem was, finding where the ball lands, or you had the Galton board and the ball lands. Instead of computing it by pen and paper, we were able to build a photon system that does it much faster for us. In the second example, instead of, just doing a lot of calculations and finding what's the minimum way to cover that area, we've just built a soap film, built a wire for a soap film and made that solve the problem. But as you can see, it's not straightforward to build these things. So it's important to find good ways to restate the computational problem so that a quantum system can solve it for us. So I think that's a major challenge in itself. We do not face in classical computing because classical computers are much better at general purpose tasks. So yeah, I think that is yeah, I think that that's the end of today's section. So again, tomorrow I will continue the rest of the things in the outline, but think that covers. I think I'm a little ahead of time because yeah, in case there are any questions, we still have time for that. So, but yeah, that's the end of it for today. And any questions? Yeah, it's okay. You know, you can ask any question. It's okay. Any question is okay. And like I said, even if I'm not able to answer it today, you know, you can ask it today so that I have time to look at it and hopefully answer it tomorrow. So yeah, feel free to ask me any questions on this.
So, sir, I think participants was clear about your topics which we have explained.
Yeah, yeah.
They are not having any doubts. Yeah, it's very informative, sir. Your session.
Yeah, thank you. I hope it was. Yeah, thanks a lot for having me. Yeah, thank you. I mean, I hope I managed to, you know, convey useful information, and I hope it was useful to you. I mean, like I said, if you can think about the topic, and like, you know, if you have any questions, you guys can ask tomorrow as well. I'll cover the remaining topics tomorrow, and you know, I can share the slides too if you want. But yeah, like I mean, yeah, you can think about these topics, and even tomorrow I'll be here covering the rest of the topics, and you can ask me any questions tomorrow as well.
Yes, sir. If you want to share the slides, means here I am providing the mail ID, sir.
Okay, sure. Yeah. Yeah, thank you for having me.
Yes, sir. I have sent the mail ID in chat, sir. You can share the PPT to me. We will share it to the participants also, sir. All of
Oh,
them.
sure, I'll do that. Yeah, yeah.
Yes.